Assalamu alaikum students. Article for today is torque acting on current carrying loop or a coil. You must have read in first year that how torque is acting on a rigid body. Torque is basically the turning effect of force. So here we are going to see that what will happen if there is a current carrying loop and we are going to place that current carrying loop in a uniform magnetic field, how torque is going to produce in that current carrying loop. So this is the basic thing which we are going to learn today. Here we can see that firstly we will discuss the principle, that what is the principle behind this torque. The principle says that if a current carrying rectangular coil or in any shape, the coil is placed in a uniform magnetic field, it experiences force and torque ultimately, right? So how and ultimately that coil is going to rotate. This is the basic phenomena because of which our many appliances work. What are those appliances and what are the practical applications, I will discuss at the end of the lecture. Now coming towards the derivation part for this, so first we need to understand the whole figure concept of that how the forces are acting on the coil, and then we will go for the derivation stuff, that we will calculate the magnitude of the forces. So moving ahead, we need to determine the forces that are acting on the current carrying coil. So here you can see in this figure that I have taken a rectangular loop, and this rectangular loop of one side I'm taking its length to be A, and for the other side its length taken to B, or you can say width taken to be B. So these are the two lengths chosen, and I have given the name PQRS to this coil, and this coil is placed in a magnetic field such that there is the north pole of the mirror magnet, and here is the south pole of the mirror magnet. So that's how the field is going to be like this, or you can use an electromagnet for this purpose as well, right? Now we see that this rectangular coil is basically mounted on a shaft. Definitely when this coil will rotate, this will be the axis of rotation. This shaft would be the axis of rotation about which this coil is going to be rotated. Direction of current has been shown that the direction which we have chosen here is the clockwise direction, and now from this configuration at any because we cannot calculate the current for this whole area, so we are going to divide it in different lengths, like PQ, then QR, and then RS, and then SP. So for all the sides we are going to get the magnitude and direction of force separately, and then we will add all of them, right? So for this thing, starting with the side PQ, the same formula that is acting on the force acting on the current carrying wire. So using the same formula, we have F equals to BIL sine theta. Now here we can see that magnetic field supplied is B, current flowing is I, and what about L? We are not having L here, we are having A length of the wire, or the side Q, PQ. So I'm going to write A over here, and now coming towards sine theta. So here we see that the value of theta in this case is 90 degree. How? Because the direction of this L element is, or you can say A element is in the upward direction, and it is making an angle of 90 degree with the magnetic field. So that's why I have put 90 degree over here, and the answer which comes out to be, it would be BIA, because sine 90 degree is equal to 0. Now choosing the same side, that is FRS. Why I'm going to solve RS first, because this is exactly like PQ. So definitely here the angle would be the same, again you can see this angle would be the same, that is of 90 degree. So the equation would ultimately become BIA. So here we see that calculating the value for FRS, we are having BIA sine 90 and the value would be again BIA. So from here we see that in terms of magnitude, FPQ and FRS, they are equal to each other. Now coming towards the sides, QR and PS. Now I'm going to calculate the magnitude of these two forces. Uh, so here you can see that I have calculated FQR, whose value is going to be BIB sine theta. Why B? I'm going to put here the small b, because the length of this side has been taken to be B. Since we don't know the angle for the side QR, which is it making with the um, magnetic field, since this angle theta, we don't know this angle, so because of that thing, we are not going to put any value for this, and simply we will, or this value of theta, simply we will put the same values in both situations. So FSB, it would be again having the same value, BIB sine theta. We don't know the value of theta, so these values would remain like this. So here we notice that the magnitude of FQR and FSP are same to each other. So we see that the forces, if I give the names to them, these are considered to be, if this is like F1, like suppose if this is the force that I'm going to take as F1, and this is the force that I'm going to take as F3. Obviously it is coming after QR, so that's why I'm giving it name as F3. Now this FQR, this is force F2, and this is the force F4. So we see that the magnitude of F1 and F3 are same, and the magnitude of F2 and F4 are same. So in terms of magnitude they are same. Now what happened to their direction? Does the direction are same or different to each other? So to consider that factor, what are we going to see? Okay, now we are going to find out the direction of force which is acting on the side PQ. For this we see that the direction of a magnetic field is towards the right side. So using the Fleming's left hand rule, I'm going to direct my um, forefinger in the direction of this magnetic field. So this is the direction of magnetic field that is indicated by the forefinger. Now if I want to see the direction of the length element, which is which is in the upward direction, so if I'm going to draw this, I would draw it like this. This is the direction of the length element, that is L. Now the last thing that if I want to determine the direction of force here, it would be definitely perpendicular to both of them, since L and B are in use. So force would be directed inward, that is into the page or into the screen. So that's how this is the direction of force which would be experienced by this loop, by this side PQ. So I'm going to draw this like this. This is F1, direction of F1, and I can also draw it by drawing simply a cross. Why I'm drawing a cross? Because we have already read that cross indicates the field or the force, anything which is into the page, right? So that's how this cross represents that F1 is directed into the page. Now coming towards the next side, RS, for this side we notice that the direction of B is again towards the right side. So using the Fleming's left hand rule, putting my forefinger in the direction of magnetic field, and my middle finger, it is going to represent the direction of current, which is downward. And now we see that our thumb indicates the direction of the force, and this direction which is it indicating is basically out of the screen or out of the page. So if I want to draw this, I can draw it like this. This is the direction of force that is in the z-axis again, and this is the direction of force. Now if I want to draw this force, I can draw it like this. This is the direction of force, that is f3, which we had named earlier. And if I want to draw it in a more simplified form, so I can use a dot over here just to represent the direction of this force, that it is acting out of the page or out of the screen. Now the next side, which is the side QR. So for the side QR, we see that the direction of B is again towards the right side, and here L is not perpendicular to B, which is the basic condition of Fleming's left hand rule, that L and B should be perpendicular to each other. Since L is not perpendicular to B here, it is making an angle theta. So what I'm going to do, I'm going to resolve this L into its rectangular components. Now if I draw the rectangular components of L, it would, I have drawn Ly and Lx, and you can see that this vector is making an angle theta. So Lx is in the direction of B, and Ly is basically into the page. When Ly is into the page, that means this Ly is making an angle of 90 degree with B. So Ly component is the component which is going to produce force over here, right? Ly, the if I am going to use my middle finger for L in the direction of Ly, which is into the page, right? I'm going to show it over here that the direction of Ly is into the page, right? Okay, so Ly is into the page, and the direction of magnetic field is towards the right side. Then the force experienced, it would be in the downward direction, right? So here F2 is acting downward. So if I'm going to draw this, it would be like this. F2 is acting like this, right? Now for the last side, which is SP. So here you see that L is making an angle again theta with the B. So definitely I'm not going to solve it with the help of Fleming's left hand rule. To determine the force, we need to resolve this L into its rectangular component. So the rectangular components of L will be like, so here we see that Lx and Ly have been drawn, and you see this Ly component is basically drawn out of the page, right? Its direction is basically out of the page, right? So when it is out of the page, and it is making an angle of 90 degree over here, same as it was making an angle of 90 degree here. So here we are noticing that this Ly component is going to play the role for producing the force. So my middle finger is in the direction of Ly, which is out of the page or out of the screen. My forefinger is in the direction of magnetic field, which is towards the right side. Then thumb will indicate the direction of the force. So using the Fleming left hand rule, we see that the direction of F4 is in the upside direction. So here if I draw the direction of this F4, this is acting upward, right? So these are the different directions for the forces acting along the whole of the sides of the coil. Here we are noticing that F1 and F2, which were earlier, we have seen that the magnitude of F1 and not 2, 3, F1 and F3, they were having magnitude equal to each other. Now here we are noticing that the direction of these two forces are opposite to each other. Their magnitude was same, but their direction is opposite. How it is opposite? F1 is directed into the page and F3 is directed out of the page. That means they are completely opposite to each other. Talking about F2 and F4, F2 and F4 are the two forces which were having magnitude equal to each other, and we see that the direction of them is completely opposite to each other. So F2 and F4, F2 is in the downward direction, F4 is in the upward direction. So we see that these two forces are also opposite to each other. Now if I really want to show this with the formula stuff, coming back to the slide, we see that FPQ was directed into the page, and FRS, it was directed out of the page, right? So we see that, right? So FR is directed out of the page. FQR was the force which was acting downward, and FSP is the force which is acting upward. So that's how we see that the both forces, they are having equal magnitude but opposite in direction. And similarly on the other two sides, that is for the B, we are having FQR equals to FSP, and they are again opposite to each other. Now moving towards that how this coil is going to be rotated. So for that, so here I'm mentioning that couple produces rotation. What is basically couple? There are certain conditions for a couple. Every force cannot produce rotation. How couple generates? There are basically three conditions for a couple which necessarily to be fulfilled if we want anybody to produce some kind of rotation. But before that, we know that the sum of all the forces, that is the first condition of equilibrium, sum of all the forces should be equal to 0. Now here we notice, if talking about the previous slide in which we have computed all the forces, if I'm going to sum all the forces, what would be the sum? It would be like, for the first side, the magnitude was B I A, and for the side the third side, for the third side the value was, since now we are having directions as well, we see that the direction of both are opposite to each other, so I'm going to put a negative sign with that, BIA. For this is for us F3, this is the value of F3. Now F2, the value of F2 was IBB sine theta, so it was IBB sine theta, right? And since F4 was completely opposite to opposite to this force, so I'm going to put a negative sign with that. So here we notice that I have put all the values, and we see that this force is cancelled by this force, and this force is cancelled by this force. So ultimately we see that the sum of the forces in this case is equal to 0, right? Now the question arises here, if summation F is equal to 0, that obviously means that there will be no linear motion, right? So if there is no linear motion, as we can see that the coil is not moving in any or accelerating in any direction, so what is going to happen with this coil? Torque is going to produce here, right? Since we say that if summation F is equal to 0, does that mean the summation tau is also equal to 0? So no, the answer is no. Why? Because for the sides, that is F1 and F3, they are going to produce the torque, and the sides, for these sides we will notice that the direction of a couple will produce, right? And how this couple is going to be produced, moving ahead towards that. So as you can see in this figure, this is basically the top view of the coil. um, what is meant by the top view. If you are using the computer screen or the mobile screen, just simply tilt your mobile phone or the screen of that in a direction towards you, right? When you will tilt it, you will notice that you can see a single line now, right? So that's how, when we observe this coil from the top, from the very above of the coil, we will going to see this a single line, which is the side B, right? And as we know that the forces which were acting on the 2 points, like the side that is QR, those forces, if I really want to draw those forces, I can draw them like this. If I observe from this top view, the forces, the direction of force would be like this, right? So here you can see the direction of the forces F1 and F3. F1 is acting into the page, but through the top view, if I observe it, it would be like moving ahead, and that is moving away from us. And in top view, if I observe F3, it would be like towards me. So this is from the top view. Now moving ahead, and how we say that couple is going to be produced, since the formula for torque is equal to R cross F. But here we notice that we are not having the case when R, sorry, not R here, there would be B in this situation, because we have taken the length to be B. So here B is not perpendicular to F, right? We are like not in the condition when B is perpendicular to F, as you have read earlier in your previous classes. And this is not the condition here. Actually, B is making a certain angle with the force. So for this reason, what are we going to do? As you can see here, that in this situation, I observe that how we are going to calculate this couple arm. So I'm going to resolve my B vector into its components. Now if I resolve it into its components, they can be drawn like this. This is one of the component, right? And this is the other component, right? Now we notice that these two components which I have drawn these two components, but there is a problem. I'm not sure that what side it could be. So just to have a confirmation, what I see, that here we are having an angle theta, which is equal to 90 degree. And now to know where is the angle theta is, because where there is an angle theta and 90 degree, that could be the base. So to know that thing, what I'm going to do here, I'm going to draw this perpendicular, right? What this perpendicular is representing, this is the perpendicular on the surface, so this is going to represent the direction of the area, direction of the surface area. So this surface area is making an angle theta with the magnetic field, right? This is the angle theta it is making, right? Now we know that this whole of the angle, this whole angle, this is of 90 degree, right? If this whole angle is 90 degree and we are having theta over here, like this is the theta and this is 90 degree, then what this angle is going to be, the value of this angle, right? So the value of this angle would be 90 minus theta. If this is angle theta, then the same angle would be drawn over here, that is angle theta, right? So in this regard, why we are doing this, because the angle drawn, which is drawing basically a perpendicular over a surface, and we have drawn this angle to be theta, so the same angle would be existing here as well. So here is theta, here is 90 degrees, so that means this is going to be the um this is going to be the so here you are noticing that the component which is perpendicular to the force is basically b cos theta, and this is the component which is responsible for producing torque, for generating the couple arm. So here b cos theta into f, now putting the value of f, what I get, b cos theta into f, and the value of f was b I into a, right? um, so the value of this BIA, since the magnitude was same, so taking the either of the forces on side PQ or on the side RS, so accordingly we are having tau equals to just a little interchange of the a little rearrangement of the values, BI into AB, this B, and here we are having this cos theta. Now here you are noticing this AB, these are the length and the width of the rectangular coil, so the final formula would become BIA, that is the surface area, cos of theta. Now you must be wondering where this a comes, and from this theta. This theta is basically the angle which is lying between b and a. So if I've been asked to find out the final the value of torque, it would be, so this is the final formula, that is NIA cross B, where A is the vector area and B is the magnetic field. N is the number of loops or number of turns of the coil, and I is the current. So here we are noticing that theta is the angle between A and B, that is the vector area, and B, which I had shown here with this blue arrowhead. This is the direction of a vector area. Now coming towards the fact that on which factors or you can say on which factors this couple would going to be depend, but before that I would love to tell you that in what are the special conditions, or you can say what would be the special cases in which torque is going to be the maximum and it's going to be the minimum. So we are here, I have drawn a case in which this coil is basically lying completely parallel to the magnetic field, right? Just consider that this is lying on the surface, right? So when it is lying on the surface, it is making an angle of 90 degree with the B. How can I show this? If I'm going to draw vector area for this, it would be in this direction, that is out of the page, right? So this area which is out of the page, it is going to make an angle of, this is 90 degree, that is it is perpendicular to the direction of B, or you can say surface area, simple area, is parallel to B. So for both these cases, what is going to happen, that theta would be equal to 90 degree, and when theta is equal to 90 degree and cos 90 degree gives you the value equal to 1, so in this case the torque which is observed, it would be the maximum, right? For the next condition, so here you can notice that I have simply drawn this coil just like this, that this coil is now at a completely 90 degree to the magnetic field, right? So it is completely in the standing position. So in this condition, what is going to happen, we can say that if I really want to draw the direction of vector area, I would have to draw a normal on this point. So the direction of normal, it would be like a is, again we see that here it is parallel to b. And when it comes to surface area, so we notice that in terms of surface area, it is perpendicular to b, right? We have already discussed what is meant by vector area and what is meant by surface area. You already know these things. And now in that condition, theta would be equal to 0 degree, and we know that cos 0 degree gives you the value equals to 1. Okay, so here we have taken the two conditions in which the coil is taken to be lying parallel to the magnetic field, right? It is completely lying parallel to the magnetic field, and in that condition, we see that the whole of the coil is basically parallel to the magnetic field. So theta in this regard would be equal to 0 degree. So in this case, what you get the torque to be maximum, since cos 0 degree gives you the value equal to 1, right? Now coming towards the second circumstance, in which we see that the coil is basically standing vertically in the magnetic field. In this condition, we see that the surface area is basically perpendicular to the magnetic field. When surface area is perpendicular to the magnetic field, so in this condition, theta would be equal to 90 degree. So in this regard, we see that the torque would be equal to be 0, since cos 90 degree gives you the value equals to 0. Since this is the angle which is between the length L, or you can say the length A, and the magnetic field B, right? So if this length, the length is here, it is taken to be A. So this is the angle between A and B. Here as well, this is the angle between A and B, right? As A here is in this direction, right? Direction of A is like this. So accordingly, what we are having, that this whole coil is can be calculated, the torque for the whole coil can be calculated like this. But what would be the condition if I talk about the vector area? Now if I want to talk about the vector area, what is going to happen, that so this is the condition in which we have taken B at an angle of some theta along with the direction of B, right? In this condition, now if I want to draw a perpendicular on this vector area, on this particular length, that is at this green color arrowhead is indicating the direction of the normal. So if I talk about this normal, what angle it this vector area is making with the magnetic field, it is making an angle alpha, right? Now consider the thing that this whole angle is basically 90 degree, right? So if I write the equation, so here we can see that tau is equal to iba cos theta, and the value of this theta, if I want to get it, I know that this L and A, they are at an angle of 90 degree completely. So if I subtract this alpha from 90 degree, what is going to left, that is theta. So instead of this theta, I am going to write 90 degree minus alpha like this. And when we solve this particular value, that is cos 90 degree minus alpha, this comes out to be sine alpha, right? Now this alpha angle, how it is going to provide you the required results according to the vector area. Now talking about the vector area, since on this first figure, as we observe that here the direction of vector area is going to be out of the page, right? So here if it is out of the page, we see that for this out of the page means that it is moving towards me, right, towards you or towards me, out of the page, out of the screen, and it is making an angle of 90 degree with the magnetic field, which is in the direction right side. So for this case, now alpha is going to be equal to 90 degree, and if I put the value of 90 degree in this formula, then torque is going to be maximum, right? So that's how we calculate the value of torque in this case. Now coming towards the next thing, next example in which the coil was standing in this condition. If I'm going to draw the direction of vector area, it would be like this, right? This is the direction of vector area, and now you see that the direction between A and B, it is going to be 0 degree. So if I put the value of alpha equals to 0 degree, what I get tau equals to 0. Why it is equals to 0? Because sine 0 degree gives you the value equals to 0. So that's how we can use our vector area using the formula tau equals to IBA sine alpha. And if I want to calculate the torque with the help of this line element, that is L, then we have to choose the angle that is theta, and we will use the formula tau equals to IBA cos of theta. So this was the same procedure which is not given in your book, but I have mentioned over here. Now there's another question that comes into mind, that why F2 and F4 do not form any couple. There were four forces. One force that was F1, and that F1 was acting completely into the page, right? And so these kinds of forces that we had observed. And now the condition of couple is, which I was talking about, which I was earlier talking about. There are three conditions for a couple. And number one condition, that the magnitude of the two forces should be equal, right? So if we talk about magnitude, then we notice that the magnitude of F1 and F3, it was same, and in terms of magnitude of F2 and F4, it was also same. So the first condition, which is magnitude, all the four forces, it fulfilling this condition. Now the second condition for producing this couple is basically off direction, right? That the direction should be opposite. Direction of the two forces should be opposite. So if I notice that direction of F1 and F3, these are again opposite, and F2 and F4, these are also opposite to each other. Okay, so the third condition is that the two forces should act on different points of the same body, right? F2 and F4 are the two forces which are equal in magnitude, opposite in direction, but they are acting on along the same line of action, right? So F2 and F4, they are having same line of action of force, that is, they are acting on the same points on the same body, right? But F1 and F3, they are having a distance equals to d, and F1 is acting in this direction, F3 is acting in this direction. So they are equal in magnitude, opposite in direction, and also acting on the same body but at two different points. So the main condition for couple is that the F1 and F3, they should be acting on two different points of the same body. So here the condition of couple is fulfilled, so F1 and F3 are going to produce the couple, and F2 and F4, these are not going to take any part in producing couple, rather they will try to compress the coil, as it is mentioned in your book that F2 and F4 are the two forces which are going to compress the coil. Since the magnitude of both the forces is equal in direction opposite, so they are not going to successful in that, and ultimately the spring not the coil is not going to be compressed, but they will try to do so. So that's all for couple, the question that is regarding couple. Now the last thing which you should know is about the dependence of torque, right? So the factors on which this torque is going to depend is, firstly, using the same formula, we are having n, that is the number of turns, or you can say the number of coils. Then comes the magnetic field, then comes the cross sectional area, sorry, the surface area, then comes the current, and last but not the least, we are having theta, between A and B, right? So here we notice that this torque, if we are increasing the number of turns, definitely torque is going to increase. More magnetic field, more torque; greater surface area, greater torque. But while we are performing a particular experiment, these three terms, they are kept to be constant, right? And to variation which we want, we change these two values, right? So the variation occurs in theta and in this I. These two quantities are variable quantities. Simply, this phenomena is observable in the regulators of the fans, the speed of the motors, and in the case of galvanometer as well, which we are going to study in the next article. In all of these, we are changing basically. In galvanometer, we are going to change this I, and accordingly theta is going to be changed. And when theta is changing, I also changes. And in case of applications, we, as I have already discussed, the applications are that can be any motor. The construction of motor is just like this. You are supplying the current and that particular coil starts rotating. This phenomena is everywhere, existing everywhere. All the appliances which are using motors, for example fan, and in that fan, what actually happens, there is an electromagnet, and when we are increasing, we are changing the regulator, then basically what are we doing? We are basically increasing the current. When we are increasing the current, the torque is going to be produced in a greater amount. So in that regard, that's how fan is also an example of that, and there are many more examples everywhere. When it comes to motors, obviously you will get to know about the torque. So that's all for today's article. Thank you so much. Allah Hafiz.